This is section 7.3, fixing Ampere's law. All right, fixing Ampere suggests that Ampere's law is wrong. Well, under what context is Ampere's law wrong? I know that Ampere's law tells me that the curl of my magnetic field is related to mu naught times my current density. Okay, and for most of the time we say, all right, well, I have a wire. That wire carries some current. I am going to draw an Amperian loop around that wire. I'm going to integrate all of the magnetic field that goes around that loop, and that is equal to mu naught times I enclosed. Okay, and I enclosed is often interpreted as the amount of current that's piercing the surface. So it's mu naught J dA. Specifically, when I think about the current that's piercing the surface, it's the surface that's bounded by the loop that I've defined, right? So we've been writing it as something like this. Okay, so all of the current that goes through that green area is the current that goes through the surface, and that's fine. Okay, and we did this because it's the simplest possible surface for our loop. But it's not the only surface. What if I have a loop that looks like this? I can go ahead and define that simple surface like I did before, but there's also other surfaces. There's an infinite number of other surfaces that are bounded by that edge. So if I think about that loop that I defined as being like the opening of a plastic grocery bag, right? All right, and it's any surface that's defined by that opening. Okay, those only boundaries that exist for both the purple and the green are that red little bit. Okay, so let's consider a kind of a weird scenario then. Let's go ahead and say I have a leaky capacitor in a circuit. If it's leaky, that means there's a current that's flowing through it. All right, and I can go ahead and draw an Amperian loop. All right, great. And then I'm going to, instead of defining the simplest path or the simplest surface, I'm going to go ahead and define it as the surface that goes through this capacitor. Okay. All right. So there's current flowing. That was the definition here. So since the current is flowing, there must be a magnetic field. But there is no current that is piercing that surface. Right. The way that I've defined this green surface, there's no part of that wire goes through it. Okay. But there's no current piercing the surface. That must mean that my expression for Ampere's law is not quite correct. Okay. Let's start with our the Ampere's law, mu naught J. All right, and I'm going to add an extra term here. I'm going to say that this is what our old term is, but now I have something that is related to a time varying thing, right? That's the correction here, is that our Ampere's law is correct in magnetostatics, but it's not going to be true in dynamics. So that is going to be mu naught epsilon naught, a time rate derivative of the electric field. Right? And maybe you can justify the fact that this is related to the electric field, because while in this diagram the current is flowing in the wire is not piercing the surface, but there is some buildup of charge across this capacitor. And as the current flows, the amount of charge on that decreases. So the electric field in that capacitor is also changing in time. All right, so I'm going to go ahead and take the divergence of both sides of that expression. The divergence of the cross of B is equal to the divergence mu naught J. I'm going to distribute the divergence here, plus the divergence of mu naught epsilon naught d dt. Well, this is a divergence of a curl, so that's always zero regardless of what field I'm talking about. That becomes mu naught minus d rho dt. That's our continuity equation, right? This divergence of our curl or of our current is only zero if they're in a steady current, which we aren't here. Okay, plus mu naught epsilon naught. I'll go ahead and take that time derivative out here, since the derivative of this time derivative can be done in whatever order with respect to the spatial derivative. Go ahead and bring that divergence in here. All right, now I have something that's related to the charge. Well, the charge is also related to the electric field. So that's minus mu naught d dt of whatever rho is. So rho can be written as terms of Maxwell's equation, epsilon naught del dot E, plus rho naught mu naught epsilon naught d dt of del dot E. That's zero. Oh, and these two terms are exactly the same, except there's a negative sign. So that is zero. And hopefully you appreciate the fact that I wouldn't have got 0 equals 0 if this extra term didn't exist, right? That term over here was what I needed to cancel my initial term. Okay. So this bit right here is the new version of Ampere's law. And we have to use it if we have electric fields that are changing in time.